Functions. Okay, this is turn to page 92 in your textbook. We're going to be looking at some problems that are in the homework assignment. We're going to be looking at functions. We're going to pretty much what we're going to do is we're going to look at them. We're going to identify what a function is. We're going to learn some characteristics of functions, things that happen when you deal with functions, how to identify something as a function, and domains and range are the main things that we're going to be looking at today also. To start off before functions, we got to know what a relation is. A relation is a mathematical relationship between two quantities. So again, it is a big, wide group of a bunch of different things. All kinds of things are relations. What we want to do is narrow our focus down to a thing called a function. And here is the definition of a function. It is a relation where the input value, known as the domain, for each input value, there is exactly one output value, and that's called the range. So the input values are called the domain, the output values are called the range, and for each input, there is exactly one output. That is what a function is. One of the easiest ways to determine something's a function is by looking at their graph. I'm sorry, let's look at the notation first, what this means. Function notation is written like this. It's usually a letter, lowercase, could be uppercase, it doesn't really matter. And then next to it in parentheses is a single letter. This letter right here represents the variable of the function. This letter means the name of the function. And we usually default to the first one as F because it represents a function. But we can use any letter we want. Any letter can be called a function as long as it's in this format. And it basically means the value of the function at x, and we abbreviate all that to just say this is read as f of x. It's the function whose variable is x. I want to determine if a relation is a function by looking at its graph using the vertical line test. Here's the vertical line test. If any vertical line drawn through a graph touches the curve in more than one place, then the relation is not a function. So that's the difference. Okay? So let's look at some examples of a couple of them. So if you look at problem number 6 in your textbook, you can kind of see that one. I'll draw it real quick. If I have a graph, here's the x and y axis, and the graph goes like this. These are the x values. The easiest way to look at it is, can I draw any vertical line and hit this graph more than once? If the answer is yes, this is not a function. What vertical line? Any one you want, anywhere you want. Vertical lines go up and down. So you can see clearly if I draw a vertical line right here, I hit the graph here and here, that's more than once. This is not a function. This graph represents a relation, but it is not a function. If you look at number 8, you'll see a graph that you may or may not be familiar with. And it looks something like this, and then does something like this. And so then the question is this a function or not? Well, I think it's pretty clear that no matter where I draw it out here, now these go on forever. Remember, even though I didn't write it, it goes on forever. Everywhere is fine. Anywhere I draw a vertical line, it's going to be fine here. It's going to be fine over here. So the only issue that I have is right here in the middle. Okay? And the way this is drawn, even though it's kind of hard to see, is there's like a boundary line right here. And we'll talk more about that in just a moment. And that boundary line is a vertical line. And this graph gets really close to it, but it never crosses it. And this piece of the graph goes really close to it, but never crosses it. So is there any vertical line I can draw that hits the graph more than one time? And in this situation, the answer is no. Since I can't draw a vertical line and hit the graph twice, this is function. And if you look in your textbook real quickly here, for those who can't see this, but number 7 is a circle looking thing. So that would be what? A function or not? hits the graph twice, not a function. Okay? What about domain and range? Domain and range. Why do you even need to know this? Why is it such a big deal in this class? Well, we're starting to get to mathematics that is used in the real world. And in the real world, we use functions that model real life scenarios. And it's important for you to know what values are even possible or impossible in your scenario. Okay, so that's what a domain and range do. And I even put this and consider this value. An example what I'm referring to is this. If I write a function that models the number of people that go into a stadium at a certain time rate, do all the values, now if I have a function, that means I have a y equals x and all that kind of stuff. Well, mathematically, in a function equation, I can plug in a lot of different numbers. I can plug in positive numbers, I can plug in negative numbers, I can plug in 0, okay? But if I model the number of people going into a stadium for a football game or something like that, can I use every single value for x? In other words, if x represents the number of people going into the stadium, does it make any sense to have negative people? So we have what's called a restricted domain. Even though the function says I can plug in a -3, in reality, -3 people makes no sense. So that's why domains are important. And then ranges are too for the same purpose. Okay? So that's why you need to understand domain and range. What's possible and what's not. So here's some things that I want you to look at. And remember, for our purposes in here, there's very few things that are going to restrict the domain for our use in this class. Here are the main ones right here. Roots. In particularly, an even root. So if you remember, this little n up here is called the index. It tells you what kind of root you have. You can have a little number here, it means many different types of roots. The one you're most familiar with is a square root, and that just means that n was a 2. And that's the only index we don't write, is for a square root. But as long as that index value is even, I have a restricted domain. Because for every even root, okay, this number underneath cannot be negative. The radicand, that's the number underneath. Okay, everything that's in the underneath, that's the radicand. That value can never be negative for an even root, okay, in the real world. So the domain of this function, and I've written it 2 different ways. The domain is all the x's have to be greater than or equal to 0. In other words, it can't be negative. It can be 0, it can be positive, but it can't be negative. And that's how you can say it this way. Where our math is starting to lead you to now is this process right here called the interval notation. Interval notation, here's a little sidebar to it. If you use a square bracket like that, this means the endpoint is included. If you use an open bracket like that, this means the endpoint is not included. It's a boundary, but it's not included. This one with this, it's a boundary, and it is included. So look at this. See, for 0, it's greater than or equal to. So 0, since it's on the left, is the lowest number it can be, and the square bracket means it's included. This is an infinity because the numbers just keep on going forever. Infinity is not a number, it's a concept, and it is always open because you can never tell me the last number. Okay. This is an example of a rational function, otherwise a function with a fraction look, and there's an x in the bottom. In this one, because a fraction, the denominator can never be 0 in a fraction. The denominator can never be 0. So that's the only value in this one that cannot be included. And so we say that the domain is it's basically all the real numbers, x cannot equal 0. So this is the way you can write it, or you can write it in interval notation, and it would look like that. From negative infinity to 0, zero not included. This little u means union, fitting for us here. And then 0 is a boundary again, but not included, all the way up to infinity. So the only number that's excluded here would be just the 0 itself. These are your two main domain things. Almost everything else, except for some other weirder ones, would be all real numbers are most likely a domain. But we're going to look for these things to help us determine domain and range first. What about the range? The range of the y values, the output values. We in here are just going to use the calculator graph to assist us in finding the domain, finding the range. Okay, it's just easier that way. I'll explore this a little bit more for you as we move along. So we can start off though by doing an example. You can do it with me. Grab your calculator. Let's look at number 9. We're going to graph it real quick. Just do it on your calculator real quick. I'm just going to do a quick sketch of it. Or you can just watch up here, it's fine. So we had y equals, oh, they called it f of x. So this is a function, so we can call it f of x. It's x squared plus 4. It looks like this. And this point right here is at 4. So you can see, we look at the graph, we can see, well, what would the domain be? Well, here's my function. I don't see any even roots. I don't see any rational function here. So, and I can look at the graph and I can see, even though the arrows are pointing upward, they are also going outward forever and ever and ever. So the domain of this function would be all the real numbers. You can just write all real numbers, or you can write it in interval notation, and it would just be negative infinity, comma, to infinity. So that interval right there. Either one of those two ways is fine. Okay? You can choose which one you feel more comfortable with. I'm fine with either one. The range, if you look at it, this is why the graph makes it easier. What are the y values associated with this graph? So when you look at a range, or you're trying to find the range or something, it's look for the ones that it can't be. Break the number line up into 3 groups: positive numbers, negative numbers, 0. Can I get negative numbers? Well, the y values, remember ranges for y values. This is the origin. These are the negative y values. These are the positive y values. Can I get, does the graph anywhere down here in the negative realm? No. Does this graph, is it at the 0? No. In fact, it's not even in some of the positives. The lowest positive value that it is associated with, we can see right here, is at 4. And then from this point onward, going up in a positive direction is where the graph is at. So the range is all the y values starting at 4, so 4 is included, and going up. So it'd be all the y's greater than or equal to 4. That's how you can display the range. You can do it in interval notation. 4 is included, all the way up forever. So these two things are exactly the same. We will explore this in many more examples as we move along, but that's the idea right now. The next thing I want to look at is this thing called continuity. This is a big concept in the class and calculus and stuff like that. A continuous function continuity, what does that mean? I'm going to give you kind of like a working definition here, not the actual official definition from a calculus perspective. So continuity, a function is continuous if there are no breaks or gaps in its graph. Pretty much what it is. If I can draw the graph without lifting my pencil, it's continuous. Okay? So if it's not, if I have to lift my pencil or there's a break or a gap in it, what do we have? You're going to experience graphs that have a hole in it. So everything is there, but there'll be a hole in the graph, and then it continues on. This means this graph is not continuous. It has a discontinuity, and they actually label this kind as a removable discontinuity. It's removable because if I define a value for the whole, it turns continuous. Okay, that's how they make that determination. Don't worry about it. It's just a removable discontinuity. They're going to ask you for that kind of a name. Okay, so removable discontinuity means there's basically a hole in the graph. Here's a break in the graph. This is called a jump discontinuity because to get from one piece to the next, I have to jump across the gap in some fashion. So there's a break in the graph. Here also has a break in the graph. This one's an infinite discontinuity because at the point where it breaks, the graphs are going to go to infinity in some fashion. Okay? This describes something we're going to talk about in just a moment. These are discontinuity types. You want to be slightly familiar with them. Okay? The next one I want to talk about helps us and leads us towards the domain, to the range again. And that is this thing called extremas. Extrema just means the plural for extreme value. Okay? We have several types of definitions. The first one is the local extrema. Local extrema refers to local minimum and a local maximum. The other one we have is absolute or global extrema, and that just means an absolute max or an absolute min. Now I'm going to define both of those for you. Another name for local is relative. So you'll see one of these two words when you do your work. I can't remember which one the book uses. Different books use different terminology. So local or relative max basically says this. There's a y value, because that's a y value, will be greater than or equal to all the other y values, range values, in an interval around some point C. But what does that mathese really say? Let's use an example. Let's say I draw this graph that looks something like this. A local max is in a local confined area. This graph is going up, and then it peaks out, and then it comes back down. So somewhere right here at the top is a value, f of c. It occurs when x is c. Is that the highest value of all the values right around it in this localized area? Only here? Yes, it's a peak. Okay, so if a graph goes to a peak, that is called a local max. So what's the local min? Is there a value that kind of looks like something might be the lowest value in a certain area around it? Yeah, right here, correct? So right around this point, this is the lowest value of only those numbers right around it, localized. Okay, so this would be called a local minimum. So that's what those are. What's an absolute max or min? An absolute max or min means that a value is the highest value on the entire graph's domain, and or the lowest value on the entire graph. Okay. Now the thing about an absolute max or min, not all functions have one. They don't have to have one. This is an example. It does not have an absolute max or an absolute min. Because this arrow points up forever, it's going to infinity. So there is no number that's higher than any other number. Same thing for the minimum. This one goes down. But let's look at this graph. This point right here is a local minimum. Because all the points it's the lowest number for all the ones right around it. But in the entire graph itself, this point is also an absolute minimum, because that is the lowest point on the entire graph. There is no absolute max and there is no local max in this graph. So that's what the definitions mean there. Odd and even, I don't use this too often, but it is there. So if you remember from your geometry days, you talked about these things called symmetries and stuff like that. There's two types of symmetries that are involved with odd and even. We can determine it algebraically. You can also look at it graphically. A function is even if I can plug in a negative value and get the same answer as if I plugged in the positive value. Example, f of x equals x squared. This would be an even function. F of 2 is 2 squared, which is 4. F of negative 2 is a negative 2 squared, which is 4. Because they have the same value, and this works for all values of x, this is even. You can look at a graph and see if it's even, if it is symmetric about the y-axis. So in other words, if I can fold it on the y-axis and the two halves meet perfectly, it would be an even function. An odd function would be this one like this. And we can do the same thing. F of 2 is 2 to the third, which is 8. F of negative 2 is a negative 2 to the third, which is negative 8. And if a number I plug in gives me the opposite value of the positive version, see, I get opposite answers, then this is considered odd. If it's not even, if it's not odd, then it's a neither. There's many more neithers than there is odd and even, just so you know. What about graphically, what happens here? This is symmetric about the origin. So what does that mean? This is like rotational symmetry. If you think back to geometry. So in other words, if I draw a graph, and I'll show you an odd graph real quick. Here's x to the third. It looks something like this. Rotational symmetry is symmetry about the origin. It means simply this. If I pivot and turn this right around the origin, turn it around, you see I get the same graph? That's odd. That means it's an odd function. So those are those. We don't deal with those too often, but there they are because it's in your textbook. I want you to make sure you know what it is. Okay? Now these things are important. In behavior, asymptotes. As the values of the domain increase or go to infinity or decrease, meaning it goes to negative infinity. So in other words, as the x values get really large or really small, so we're looking at the x-axis, if the function takes on the characteristics of another function, then the other function is called the in behavior asymptote. What the heck does that mean? Okay. This is a look at really far away. So you can look at a graph, okay, and up close and see certain things. But if I zoom way out, that graph is going to take on the characteristics of something else. In other words, you're not going to see it, especially on the ends, because all I care about in behavior means at the end. I don't, so this realm in here, in between here, don't care. What happens way out here at infinity? So a good way to think about it is, don't even consider a value before a million. I want to know what happens when x is a million or beyond. A billion or beyond. Okay? What is that graph going to look like? That's an in behavior. Okay? At that point, you're getting really close to what it is you're looking for. So an asymptote. Okay? The most common one we're going to be dealing with, in behavior asymptote, is basically the horizontal asymptote. What is a horizontal asymptote? What are some graphs that you might remember that had a horizontal asymptote? Well, probably one that you remember the most, hopefully, is the one that looks like this. We're going to be talking about this in a little while anyway. This is an exponential graph. Y equals like, 2 to the x power. This is an exponential. But you can see up close, okay, that's kind of nice. But what happens way out here at negative infinity? What is this graph doing? It's getting smaller and smaller and smaller and smaller, getting closer and closer and closer to 0. So we usually designated asymptotes with dotted lines. This graph is getting closer to 0. So the end behavior is as x goes to negative infinity. So as x goes to negative infinity, the function y goes to 0. This graph is getting closer to the number 0. So 0 then becomes a horizontal asymptote. Now they're writing it a little bit differently, and I'm going to show you that. How it means the same thing. And so it has a horizontal asymptote y equals 0 because the y values are getting closer to 0. Far out enough, this graph right here just looks like the horizontal line y equals 0. Now, here's the notation the book is going to use. This is some old school stuff you might have done back in Algebra 2 notation. I'm not sure what you did in Algebra 2. This is using what's called a limit definition. Don't panic. Let me explain how it works. This is the limit. So what's the most most value that the y values can become? Okay. Down here, as x goes to negative infinity. See? Right there. See, it's the same line. See it? So as x goes to negative infinity, now I used y here. They're using the function f of x. I could have used f of x here just as well as they did, but I called it a y instead of an f. The y values equal a number. The y value equals a number. See it? So don't panic on that notation if it's the first time you've ever seen it. It literally means the same as this. Okay? Just be aware of that because your textbook uses this notation. If you know this notation, you can use it in a pinch. Try to learn that one because it will make your life a little bit easier later on. So y equals b is a horizontal asymptote. This is the same thing if I went to the positive side. The other kind of asymptote that we're going to be dealing with, I've kind of mentioned briefly before, these are the vertical asymptotes. These are vertical lines where infinite discontinuities occur. That was this situation. So there's a vertical line, even though it doesn't look vertical. Okay? And the graph is going to form something like this. The graphs are going to get close to it, but they're going to go downwards to a negative infinity or upwards to positive infinity and never cross this. This one is written slightly different than the other one. In this case, x is approaching a value. And that little minus sign that you see up in the top, it's kind of hard to see, I think, for some of you guys. That means the left side. The negatives are on the left. You're approaching on the left a certain value. Okay? What are the y values doing? Let me illustrate here. So here's the magic point right here, this dotted line. As I walk along this line, going in this direction, towards this point right here, towards that value, and I'm on the negative side of the x-axis, correct? Or this point, the graphs are doing what? They're going downward. They're going downward. So the limit as x approaches a value from the left, that's this, the y values are either going to go up or down. In this case, they would go down, so you use the negative infinity. So this one is the limit as x up, you can't see it, sorry. The limit as x approaches, I'll just say a from the left, that's what we're illustrating here. Illustrating right here, we're on the left side of this point. The values of the function are going to go downward to negative infinity. As I approach the same value from this direction on the x, because the x's are approaching, so I'm on the x-axis. As I get closer to this, the limit, as x approaches the value on the right, what are the y values doing? The y values are doing what? They're going upwards to infinity. So that's how you would illustrate in a limit fashion a vertical asymptote. So some things to remember. So vertical asymptotes are a vertical line, x equals values. Horizontal lines are y equals, verticals are x equals. Vertical lines, vertical asymptotes can never be crossed by the graph, ever. It is a hard boundary. Nothing crosses it, okay, at all. An in-behavior asymptote, a horizontal asymptote, that's not the same thing. In that scenario, your graph can cross it a bunch of times because all an in-behavior asymptote tells you is what characteristic does the graph take at the extreme ends of the graph. I can cross a horizontal asymptote. Some graphs don't. The one I illustrated, the exponential, that one doesn't cross, but there are other ones that do. Okay. Vertical asymptotes, hard boundaries, never cross. Horizontal asymptotes, they can be crossed and still be fine. Okay? So, I'm going to take some other examples off of this video.